In this session, we're going to make the big shift from descriptive to inferential statistics. So far, we've been using summaries of data, statistics, to describe trends. We used the mean to describe what a typical observation was like. We used the standard deviation to describe how similar observations were. We used the correlation to describe the tendency for two variables to be high or low together, and so on. Now we're going to take the next step to draw formal conclusions from data. In this session, we're going to cover the basic logic of inferential statistics. The concepts in this session are the theme for which we will be developing variations for the rest of the course. Suppose your friend Steve wants to play a game. You'll flip a coin. Every time it comes up heads, you'll pay Steve $1, and every time it comes up tails, Steve will pay you $1. Why not, you think? After all, the chances of getting a head or tail are 50-50. In the end, will be about equal in terms of winnings, so no harm in passing the time. You and Steve play 10 times, and the coin comes up heads 6 times and tails 4 times, which is kind of close to the 5 heads and 5 tails you were expecting. In the end, you're only out $2. No problem. Steve comes back the next day and asks if you want to play again. You have a lot of time to kill, so you two start flipping coins. You play 100 times, and the coin comes up heads 60 times and tails 40 times. You're out $20 and not too happy. What's the big deal? Steve asks. The coin came up heads 60% of the time, same as yesterday. That's pretty close to 50%, isn't it? Why the fuss? The fuss, you say, trying to stay calm, is that you're cheating by using a weighted coin, you budding con artist. Prove it, Steve retorts. If the coin is fair, you would expect to get heads half the time and tails half the time. But that only applies in the long run. For any short sequence of coin flips, you might get more heads or more tails. But the more heads you get in any sequence, the more unusual that sequence is. Out of 10 flips, the chances of getting 6 or more heads is 17%. That is, if all the students at the university paired off to play this game 10 times, then 17% of them would have 6 or more heads. So, when you had 6 heads out of 10 yesterday, it was perhaps a little unlucky, but not so very unusual. But, due to the law of large numbers, the longer the sequence, the closer the cumulative proportion should be to the true probability. If the coin is fair, that means the more you play, the closer the proportion of heads should get to 50%. Out of 100 flips, the chances of getting 60 or more heads is less than 2%. It's certainly still possible, but much less likely than getting 6 out of 10 heads. Either you were very unlucky today, that's certainly a possibility, or Steve is cheating. This is the big idea behind statistical inference. You start with some notion about how things are, like this is a fair coin. Then you ask how unusual it would be to observe the data you have if that notion really were true. If it isn't so unusual, you can keep holding to your notion about the world. The coin seems fair enough. But if the data would be rather unusual, you have some evidence to suggest that the notion isn't true. This coin is rigged. How do you know if the data you observed are unusual? You look at the sampling distribution of a test statistic. The sampling distribution tells you how likely it would be to get any particular value for the sample mean or the sample proportion from studies like the one you're doing. It's the sampling distribution that we'll use to determine if the sample from this study is unusual. Statistical inference can be broken down into 5 steps. First, there are some assumptions. Second, you look at hypotheses. Third, you compute the test statistic. Fourth, you find something called the p-value. And then finally, you draw a conclusion. Every statistical test that we'll do follows this general form, but the details for any given step will vary from test to test. Let's look at each step in a little more detail. First, there are the assumptions. These are conditions that must be true for the test to be valid. Statistical inference is based on probability theory, and there are certain conditions that must be met for the probability theory to apply. Different tests rely on different assumptions, so the first step is to know the assumptions for the test you'd like to perform and to check whether the assumptions are reasonable for the given problem. Just like some statistics are more robust to outliers than others, some tests are actually robust to violations of their assumptions under certain conditions. Next, each test has clearly defined hypotheses. In statistics, a hypothesis is a statement about a population parameter. hypotheses will always come in pairs that are opposites. One hypothesis is going to be the null hypothesis. In statistical notation, we write this as H0, with the 0 as a subscript. The null hypothesis is the hypothesis of no effect, or no difference, or no association. Nothing interesting is going on. For example, this is a fair coin. That is, the probability of a head is 50%. Or the mean income is $500. Or there's no difference in the mean income for men and women. Or the correlation between weight and the number of sit-ups an athlete can do is 0. That is to say, there's no association. The null hypothesis is that notion about the world I was talking about earlier, the idea that nothing unusual is happening. In our statistical test, we're going to suppose, for the sake of argument, that the null hypothesis is true, and then we'll look to see how unusual our data would be if that really were the case. The second hypothesis in the pair is the alternative hypothesis. In statistical notation, we often write this as H with a subscript A, or sometimes you'll see it with H with a subscript number like H1 or H2, something other than a 0. The alternative hypothesis is the opposite of the null hypothesis. It's the hypothesis that something interesting is happening. For example, the coin is weighted, that is, the probability of a head is greater than 50%, or the mean income is greater than $500, or the mean income for men is different than the mean income of women, or the correlation between weight and the number of sit-ups an athlete can do is not 0, that is, there is an association. The alternative hypothesis is generally what we're interested in knowing, but in statistical inference, we can never prove the alternative hypothesis. We can only find evidence to suggest that the null hypothesis would be unlikely. Since the alternative hypothesis is the opposite of the null hypothesis, if the null hypothesis is unlikely, then we might start to believe the alternative hypothesis. The hypotheses are statements about a population parameter, but we generally don't know the parameter, so we use a statistic from a sample to estimate the parameter. Calculating this statistic is the next step for a statistical test. But in a statistical test, we don't just want any statistic. Rather, we're looking for a summary of how unusual the data would be if the null hypothesis were true. So for each test, we have a particular test statistic. This is a measure of how different what we found in this study was from what we would have expected if the null hypothesis were true. Test statistics are generally in the form of a standardized score, or a z-score. For example, if the null hypothesis is that the mean income for men and women is the same, the test statistic would be the standardized difference, or the z-score difference, of the sample means for men and women. The larger the difference, the more unusual the null hypothesis of no difference would be. We'll look at the specific test statistics when we get into each type of statistical test. Once we have our test statistic, we need to know exactly how unusual it would be to get these results. For example, how unusual it is to get 60 out of 100 heads if the coin really is fair. To do this, we compare the test statistic to its sampling distribution and find the tail probability, which is called the p-value. The p-value is the tail probability of the sampling distribution for the test statistic. In other words, the p-value is how likely it would be to see the results at least this different from what we would expect if the null hypothesis really were true. For example, in the game with Steve, the p-value for the first game was 17%, and the p-value for the second game was 2%. Why do we look at the tail probability? In the sampling distribution, most of the observations are going to be near the center. For example, suppose we're looking at the difference between mean salaries of men and women. If men and women really do have the same salaries on average, then the difference in the mean salaries in any given sample is going to be close to 0. It won't be exactly 0, but it'll be close. Large differences in the sample means would be unusual, and those large differences are out at the tails of the distribution. The tails are where the unusual values are, so if we're looking for how unusual the sample would be if the null hypothesis were true, we need to see how far out into the tails of the sampling distribution the test statistic is. So how can we interpret the p-value? It goes something like this. If the null hypothesis were true, then p% of studies like this one would have results at least this large. For any given problem, fill in these underlined pieces with the particulars from that problem. So for example, in the game with Steve, if the coin really were fair, that's the null hypothesis, then only 2% of games like this one, that's the p-value, would have 60 or more heads. Those are the results that we got. Finally, once we've determined how unusual the data would be if the null hypothesis were true, we can make our conclusion. This is our decision about the hypotheses based on how surprising the results would be if the null hypothesis were true. If the data wouldn't be all that unlikely, that is, if we have a large p-value, we can continue along believing the null hypothesis. We don't have any particular reason to be suspicious. The coin seems fair enough. But if the data would be very unlikely, that is, if we have a small p-value, we have evidence to support the alternative hypothesis. How small is small? Often, social scientists will use 0.05 as a cutoff. If p is less than 0.05, less than 5%, we'll call the data unusual and favor the alternative hypothesis.